Okay, recording it and start recording from here. Where? Okay, here. Now we are starting. Okay. Okay. Things can happen. So my sectors may go bad. So how would you understand that? How would you understand that your sector is bad? How do you know that sector is not writable or readable? Tell me a simple algorithm.
Parity check.
Say it again.
Parity check. So
Parity check. Yeah, you mean that go to the sector, okay, read the data and check with the ECC field. If they are matching up, then you are fine. Okay, of course, yeah, that's one thing. But that may not tell you if the sector is bad, right? That will tell you that your data is wrong. That's one thing. Your data is wrong because of maybe some crash. Maybe while you are writing to your sector, you didn't have time to update your ECC field and your system crashed, right? That doesn't mean that your sector is bad physically. That means that your data is bad. So tell me an algorithm, tell me an algorithm that will give you if your sector is bad. Any ideas?
try to write a 0 at the end of a sector. If it's right, it's good. If it doesn't write, then there's something wrong with it.
How do you know that it doesn't write? How do you know that it doesn't write? This is a very simple question, people. Okay, I will check with people. I cannot code. Okay, I will do this then. I will here, so I will make random. I will make random people picks. Okay, I have only 75 people. I have only 76 people and do this and okay, here. Serdar Karakash. Tell me, Serdar, how do you know that if your sector is physically bad, it is not usable? Where did Serdar go? Where is Serdar? I lost Serdar. Okay, Serdar, I am not asking question to you now. I am asking question to Janer. Because I think Serdar is not logged on. Janer, are you here? Janer Karakash? Janer, do you hear me? Is he hearing me? Do you guys hear Janer? No, I think he logged on and he logged on and
He's writing to message chat box.
what does he say?
He say I don't know. He doesn't know.
No, he has to know and he has to use his microphone. Janer, use your microphone to tell me what you think about this problem. Janer, open your microphone. İlhan, are you here?
İsmi duyuyor musunuz?
Janer, yeah, I hear you.
I don't know this
You
question.
know, yes, you do. You are not supposed to know. I am asking you a question. You are supposed to know. This is a very simple question. I didn't tell you anything about this. I am just asking a question. It's like 2 plus 2. You cannot tell me that you don't know.
But I don't know.
So what is the question then? Tell me the question.
Error something.
What is the question? Tell me the question.
Error something?
What is error something? Is that the question? Error something?
No.
So you were not listening. Okay. Can I just log out? I mean, if you are not listening, just log out.
Yok hocam, aslında dinledim de soruyu anlamadığım için bilmediğimi
Then
söylüyorum.
why don't you ask me the question? I mean, why are you talking in Turkish? Okay, I'm asking the question again. How do you know? How do you know a sector is physically bad? Usama said that I would know if the data is bad by looking at the checksum field. And I said that, okay, that's a good way to understand if the data is bad. I am asking you, how do you know if the sector is bad? It's very related.
So can I answer?
Who is talking, Mohammed? Just a minute, Mohammed. Let me talk to Janer.
Okay.
I don't know, people. I mean, why are you logged on? You are not listening to my questions. You are not listening to me. I only talk to just 2 people. Okay, Mohammed, you tell me. I don't know why are you doing this? Okay, Mohammed.
Sir, is there a place in the sector fields that can be marked as bad for the operating system to understand?
Yeah, well, yes, you could do that in the preamble, but before doing that, you need to know that if the sector is bad.
Oh, I see.
Is it something related to disk arm? I mean, in the reading process, if the arm cannot read the sector physically?
Well, it might be because of the disk arm or anything, but I like to know if I can trust that sector again. I am not trying to find the reason why that sector is bad. Okay? I am trying to understand if that sector is bad. That's it. This is what you do, people. Okay? I don't know why you are taking this so complicated. You write some data to text sector. You read it. If it is the same, then you are okay. If you do this 10 times and every time it is coming back okay, then you are fine. Otherwise, you would say that I am not getting whatever I am writing to this sector, so this sector is bad sector. And you mark it as bad. Okay? That's it. Isn't this simpler than 2 plus 2? You just write it and you just read it. That's it. Okay? So if there is a sector, okay, you run your disk check utility. This check utility does this too. It writes a number of times to the sectors and it reads it. That's why sometimes this check utility takes lots of time to finish, because it is doing this for all these sectors. If it's a bad sector, then it is supposed to be marked as bad. Okay? And making it bad sector means what? I have to come up with a way of replacing that sector. For example, I understood that sector number 7 is bad. Okay? I am not getting the same data that I am writing to it. It's a bad sector. Okay? To make up for these kind of problems, I always keep spare sectors in the same track. This is a single track. I have 30 sectors in the track, okay? but there are two sectors at the end of this track, okay, that are not used. So what I do is I need sector number 7. It is important for me to keep my information. So I mark one of these empty sectors as a backup sector, sector number 7. I keep using this one. So what is the problem with this approach? If this is a bad sector, and if I am doing this, substituting a spare for the bad sector, so I would read from 0 to 6, and if it's a sequential file, I have to wait until this one comes in front of my head, under my head. I read it, then I have to wait again to read 8. So for sequential files, it's a problem, right? For sequential files, reading this will require 2 disk rotations, and I don't like it much. So the solution might be maybe, why don't I shift all the sectors by 1, like that one? Okay, so both of them are 2 alternatives to the same problem. The first one is problematic in terms of reading the sequential files. It becomes slower. Okay, and the second one is problematic. Why? Because you need to shift all the data on the same sector, so this will take time. Read all of them and write it to the next one. Okay, so this is one just simple error handling case. Okay, any questions on this? Anything in this chapter? Okay, chapter number 5. I did not say a single complicated thing. They are all simple. You don't have to remember anything. You just listen to me, and when I ask a question, you just interpret it and give me an answer. I mean, your answer is automatically, I don't know. You are not listening even to the question. Okay? So this is how you do the error handling. There are other ways of course, handling errors in disks. For example, there is a technique called stable storage. This stable storage uses pair of identical disks. Okay, it is different from the RAID. It is simpler than the RAID, and basically this is what we do. Okay, disk 1 and disk 2 are exact copies of the same thing. And when I write to disk 1, I write the same information to disk 2, but I don't write it at the same time. Remember, in RAID, I write them as at the same time. Okay, so why am I doing this? I am not writing at the same time. This is the reason. Suppose I am writing to the disk. I am writing to the disk a new information. Before I write to the first disk, a crash has occurred. Okay, so my old disk 1 and 2 have the same information, so they are stable. Okay, I know I did not write anything, but at least I know that my information is stable in the older version of the file system. Okay, in case B, while I am writing this new information to the disk, a crash has occurred. Okay, crash occurred and I couldn't write my entire information. So disk 1 is corrupted, but I know that disk 2 is stable. So what could I do? When I restart my system, I could get my stable data from disk number 2. Okay, and suppose in the case of C, if the crash happens in between, I write my new information to disk number 1, and my system crashed. Okay, so I have two choices now. Disk 1 is stable and disk 2 is stable too, but This one has the new information, this one has the old information. What do I do now? I could use either of them when the system restarts. Okay, and this is the case, just the opposite of case B. D and B are kind of symmetric, and E is the case that I like most. Okay, A is before I start doing stuff. B, C, D are the cases where there is an error happening. Okay, E is the way that I want it to be. Okay, I always like my data to be the same between two disks, and both of them contain the new information. This is called stable storage. Okay, I already answered this, but tell me, what is the difference between stable storage and the RAID system? Because if you remember, one of the cases for the RAID system keeps copies of two disks, right? Okay, which one was that? Okay, there are many ways of it. Okay, one of them is this, for example, RAID level 1. Okay, the other one is, well, I didn't include it in here, but with the strip based stuff. Okay, strip based stuff and the bit based stuff, I didn't include it in here, but I mean, let's look at this one. This one, RAID level 1, keeps the same information here and here. Okay, so I keep two copies of everything. So what is the difference between stable storage approach and RAID level 1? Again, you don't have to know anything about this. I am just asking the question right now. I made it up.
Can you ask again, sir? I didn't get it.
To implement the stable storage technique, what do I need? I need two disks which are copies of each other, right? RAID level 1 is doing the same thing exactly. It keeps two copies of the same data, right? Two disks. So what is the difference between stable storage approach and the RAID level 1? Isn't this considered as a RAID configuration?
Maybe the RAID configuration has like RAID controller in it.
No, I am talking something about logical. Don't go to the physical stuff.
Okay. Well, logically speaking, they seem similar. Maybe RAID they write at the same time, whereas in stable storage they write sequentially.
Yeah, that's exactly the answer. And I actually talked about this 5 minutes ago. RAID always writes in parallel, okay? Speed is important. Okay, if RAID is writing to the disks at the same time, if it crashes, then you have a problem, right? Because you are messing up both of them, because you are writing at the same time. This one doesn't do that. This one writes the first one first. Okay, make sure that it writes it correctly. Then it writes the second one. Okay, so this is definitely slower to write. Definitely slower to write. But it is more stable, because it always keeps one stable version of the data, either in disk 1 or disk 2. Okay, this is another technique, okay, for the stables. So this IO chapter number 5, as we said before, we said that at the beginning of the chapter, we said that we are going to look at the principles of IO hardware first. Okay, which we did. We talked about how the IO is done in terms of hardware, the registers and the buses and that kind of stuff. Then we talked about the principles of software, such as buffering, layering, kernel-based IO, etc. And we said that we are going to look at the individual IO devices, and we started from the disks, mechanical drives especially. Now I am going to look at some other individual IO devices, And one of the least known but one of the most important devices, okay, are the clocks, system clocks. Okay, system clocks are not typical I/O devices, okay, because with a regular I/O device, as the name implies, you either do input or output, right? You read from the input device, you write to an output device, and all the I/O devices are connected to the system bus. Clock hardware actually, okay, it is like an I/O device. It is connected to the system bus, okay, and you talk to the clock hardware using the clock driver, like the I/O device, but usually you don't get any outside world data from the clock hardware. Okay, it is a little bit different in that case, but this clock hardware is so important, system clock. Why is it so important? Because we use the clock hardware, okay, along with its driver to do this kind of important stuff. For example, we maintain the time of the day and the date. Why is the time of the day and date is important for us in the operating system? Why do we need the time of the day and the date?
For some applications, we measure the time.
Yeah, for some applications we measure the time. How long did it take? Or when we are writing a file, we would mark it. We would mark it with how many. We would mark it with the time of the creation, time of the last modification, etc. Right? Also, we need the clock hardware for preemption. Okay, when we are doing the round robin, right? We would say that, okay, you are out of your quantum time. I am going to stop you, okay? Also, we like to keep accounting information for the processes. How much time this process has used, okay? We need the clock for that, okay? And handling alarm system call from the user processes. What's an alarm system call? System alarm. I think you learned this at systems programming course, right? Alarm system call. You say that, not that one, but this one. Okay, Unix alarm system call. There is a simple function, you know this, and actually we are using this in our, okay, this is good, in our one of our homeworks. Okay, yes, so this alarm system call, you make a call alarm, you tell the number of okay, here it is. You tell the number of seconds, you say that, okay, in 5 seconds, okay, wake me up, or in 5 seconds, okay, give me a sig alarm signal. Okay, so operating system, whether you are running or not running, okay, will give you this alarm, sig alarm, okay, and you are supposed to handle it. Okay, you are supposed to handle it. How do you handle it? Okay, your sig action, whatever function you registered with sig action, let's go to sig action. Sig action is the one handled to a signal. Okay, you would say that, okay, you are going to call this function when the signal occurs. Okay, when this signal occurs. So it is automatically done by the operating system. All you need to do is you just make a alarm system call. Okay, so in 5 seconds wake me up, in 5 seconds call this function. Okay, another usage is Watchdog Timers. basically they are used for the embedded system. Sometimes a modern operating system uses them too. And other than profiling, monitoring, statistics gathering, like the accounting for CPU usage. So clock is important. That's why we are going to look at it more carefully. Okay, let's look at
Aren't the cycles itself running under the clock as well?
Say it again.
So the cycles of the CPU itself are running under the clock. So a CPU with higher clock are the CPUs that execute more instructions per second.
Well, you mean the main system oscillator? 1 gigahertz, 2 gigahertz oscillations?
Yes. Yes.
You usually know. I mean, that's a very, very low level stuff, and your clock hardware may not be connected to the main system oscillator. It might be a different one.
Yes.
But using some of the functionalities of the main system oscillators, some systems can change the clock rates and the system oscillation clock rates. But we are not talking about the main system oscillators with this one. Okay. So how does the hardware of... Yes?
Oh, okay.
Okay. So how does the clock hardware work? It works this way. Okay, very simple device. There is a oscillator, crystal oscillator. Okay. Quartz crystal. It's a material, very specific, carefully designed material. Okay, physical material. If you cut this material very carefully and put some tension on it, to put some pressure on it, and if you give it some voltage, okay, between each other, it starts giving you pulses, and these pulses are very, very precise. Okay, it can be made to generate periodic signal of a very great accuracy. Okay, so you can make it to produce, okay, one pulse every 1/1,000,000th of a second. Okay, and that's very accurate. So that's it. So that's what you do. You give a current, some kind of a current, some value of current, some voltage around this oscillator, and this oscillator starts producing pulses, maybe 1,000,000 times a second or 100 times a second. That's your design. So you get this pulse, and you use this pulse to increment a counter or decrement a counter. So every time you get a pulse from this oscillator, you decrement a counter. There is a special circuitry. Okay, so a counter is decremented at each pulse, and when this counter reaches zero, when it becomes zero, it produces an interrupt. That's what we call the timer interrupt. Okay, it produces an interrupt, and that's what we call the timer interrupt. It's a timer interrupt if this one becomes zero. As soon as this one becomes zero, there is another register. This register contains a number. This number is copied directly to this register again, and oscillator is doing the same thing. It just produces a signal, and I keep decrementing this value at each signal of the oscillator. So that means what? That means every time this number becomes zero, it produces an interrupt. An interrupt has to be handled by of course, the interrupt hardware and the operating system. Okay, and since this clock hardware is connected to the system bus, and it is connected to the interrupt handler, it is an I/O device for us then, right? I mean, it is no different than a keyboard producing an interrupt, or hard drive producing an interrupt, okay, or DMA chip producing an interrupt. It is the same thing, only the interrupt type is different. So our operating system handle this timer interrupt every time it happens. Usually, timer interrupt happens 50 times a second or 60 times a second or 100 times a second. Okay? Those are called the timer interrupts, and every time timer interrupt happens, we do many things. Okay? We do many things. Remember our memory management algorithms? Sometimes, depending on the algorithm, of course, sometimes we clear the R bits at every timer interrupts, right? Do you remember those? And at every timer interrupt, we do, regarding the scheduling, we try to see if the current process has used its quantum time altogether, right? That was related to scheduling. And sometimes we do some system updates at every timer interrupt. So timer interrupts are very important for operating systems. And timer interrupts are produced like this. So basically, you decrement this counter every time this oscillator pulses. When this becomes 0, a timer interrupt is produced. And as soon as this becomes 0, the circuitry copies this number, very large number, to this register again. And we keep doing this. So there is a complete circuit here. Okay, very simple circuit. Maybe the simplest input-output device circuit that we have looked at so far. Okay? Any questions about the clock hardware? Again, this is a very different kind of input-output device. What do you get out of this device? You don't get anything. It just produces the interrupts. That's it. It just produces the interrupts. That's it. Okay? Like other devices, keyboard produces interrupts, mouse produces interrupts, disk produces interrupts, and this one produces interrupt. When this one produces interrupt, you don't read much, okay? The important thing is that it produces these interrupts at very accurate intervals. That's the important thing. Okay, let's look at the details of this one. Okay, of course, maintaining the time of the day. So how do you do the time of day incrementation? So, okay, so you have a counter somewhere in your driver area. Okay, you just increment the counter at each clock tick. Every time an timer interrupt happens, okay, every time there is a timer interrupt happens, you increment that clock tick, okay, and that's it. And then you count the number of ticks from the system start time or from some predetermined time. So if you have a 32-bit counter, okay, and if you are incrementing this counter 60 times a second, so that this 32-bit counter will overflow in 2 years. So that means that I cannot keep time and date for more than 2 years because 32-bit will not be enough. So we should find some kind of a solution. These are part of the solutions. 64 bits, okay? 64 bits will be more than enough. Question, if 32-bit will be overflown in 2 years, how about 64 bits? 64 bits will be overflown in how many years?
Was it like 10,000 or something?
It's a large number, right? Because if 32-bit is 2 years, then 33-bit will be 4 years. 34-bit will be 8 years, right? So 2 to the power 32 more years. It will be overflown. So the 64 bits will be more than enough to keep the time of the day in ticks. Remember, this is in ticks. Okay, this is not in seconds. How do you convert the number of ticks to number of seconds?
Divide by 60.
Divide by 6, right? Yeah, that's it. Divide by 60. So some people say that this is overkill. Why are we doing this? I mean, why are we Usually the systems are like that, okay? The Unix says that I am keeping my time in clock ticks starting from January 1970, okay? Unix says that. So some people ask, why do we have to count the number of ticks? I mean, we talked about the seconds. So some people do this. They say that, okay, I am going to keep number of time of day in seconds, but to be able to more precise for the some timekeeping operations, I am going to keep the number of ticks in the current second. So this could be at most 60, but this one is I am keeping this time of day in seconds. So if my clock rate is 60 and I am using a 32-bit counter, so this one will be enough for 2 years. And if I multiply this by 60, it will be good for 120 years if I keep this 32-bit for keeping the number of seconds. So 120 years, and this one will be for precise timing operations, number of ticks in current second. And another approach is this, okay? Number of ticks, really the 32-bit, okay? And this is the system boot time. You say that I booted my system at this second, starting from 1970, but after that I am keeping everything in ticks. So as long as you don't run your computer continuously for more than 2 years, this should be enough.
Sir, how do computers then measure the time in nanoseconds, milliseconds, if it's all in ticks?
For that one, you have a special clock, okay? For that one, you have special clocks that are directly connected to your main system oscillator, okay? You get that data from there.
All right.
Okay, but the idea is the same. Basically, you ask that I/O device the current number of ticks, and you get that one. Well, basically, it is not that difficult. If there is a way to read this part of the clock hardware, right? Then you are done, right? Because this crystal oscillator is very fast. It is decrementing this number. 1 million times a second. Okay? But interrupt happens when this number becomes 0. And that happens only 50 times a second. So if there is a way to ask the clock hardware, clock driver, give me this number. What is this number? Then you are done, right? So it's a matter of reading this number. Okay. Good. So where do we use the clock, for example, for the round robin scheduling, preventing processes from running longer than allowed? Okay. Whenever a process is started, the scheduler initializes a counter. Okay. It says that this process is allowed to use, for example, five clock ticks. Okay. If every clock tick happens 50 times a second, so 5 clock tick means that 1/10 of a second. After 1/10 of a second, I will stop this one. So what do you do? At every clock interrupt, the clock driver decrements that quantum number by 1. Okay. So when you start the process, you initialize that number. And at every clock interrupt, the clock driver decrements the quantum by 1. And if that number becomes 0, then the clock driver calls the scheduler. So this is done by the clock driver. Okay. So most of the time, the clock driver doesn't let any other system procedures run. It just handles everything. It just decrements the number. Whatever needs to be done, it does it, and it just returns back to the original interrupted program. Okay? Originally interrupted program. And remember the interrupt handling, the hardware doesn't save many things, right? Hardware only saves the minimal amount of information when the interrupt happens. If the happening interrupt happens to be the timer interrupt, the clock driver is very efficient. It may not have to do anything, right? It may immediately return back to the original caller. So there won't be any very costly context switching. Or if the clock driver is decrementing a number by one, it does that and just returns. So the clock drivers and the clock interrupt handlers are very, very efficient. Okay, so don't think that every time clock interrupt happens, the scheduler will be activated and it makes a decision. Okay, so most of the time when the clock interrupt happens, okay, scheduler doesn't know that an interrupt happened at all. It only knows that the quantum time is up. Okay, good. I hope it makes sense now that we are looking at the clock software just after the disk software, disk drivers. Clock drivers, clock hardware is simple, but they are so important for the operating systems, for the scheduling, for the memory management, for the I/O stuff and everything. Okay, good. Again, as we said before, accounting for CPU usage is important. What you need to do is you start timers and you just make measurements about it. I'm not going to talk more detailed about it. Okay. And handling alarm system call from the user processes is important. But it looks like I am out of time for the first part of the lecture. Okay. So let me take 10 minutes of break. After the break, we will continue then. 10 minutes of break. Okay, alarms are other stuff that are important, and we need the clock hardware and the clock drivers to get the alarms right. Again, what is the alarm? You make a system call as a regular user. You ask the operating system to make a call for you. Okay, you say that I need to be called in 5 seconds, 10 seconds, whatever, and it calls you. And I showed you how the thing is done. So how do we implement this? Usually it is done this way. Okay, this is our current time. Let's say this is the seconds after the boot up time. Okay, we keep a linked list of alarms. Okay, and people the users ask me to make an alarm at this 4202:03 seconds and 4207, 4213, 4215 and 16 goes like that. Okay, so the current time is this, and the next alarm time is the just after 4200. I have 3 seconds now for the next alarm. Okay, every time an interrupt happens, timer interrupt, I decrement this next alarm time by 1. When this becomes 0, then that means that I got this now, right? So I produce this alarm, I handle it, and after that, after I handle this one, okay, this one goes away, this one goes away, I don't have this anymore, and then what happens? I would make this my first element in the linked list. Okay, so it goes like that. Okay, after that's why these are the differences. Okay, this is 3 plus 4 is 7. It's here. 3 plus 4 plus 6 is 13. It goes like that. Okay, this is a linked list. This is a linked list. This is a linked list implementation of these alarms. Okay, you always keep the next signal time, and when I have this at the beginning of the linked list, I put this number 4 here, number 4, and that's it. It goes like that. Okay, any questions on this? So every time I get a new system call alarm, wake me up, okay, I get that number and I place that number in between these linked list nodes. Okay, good. Any questions? Ya burada ders yapıyorum, konuşmayın ya. Okay, any questions? Okay, if there are no questions, then I will move on. Another usage for the alarms or the clock software is the Watchdog Timers. Okay, these Watchdog Timers are used very often, especially in the embedded systems. This is what happens. The Watchdog Timer is a timer, it's an alarm, okay? Usually it's a very large value. Let's say, it says that at the start up time of the system, it says to the system that wake me up in 100 seconds, okay? In 100 seconds, the system wakes up that Watchdog Timer stuff, and the responsibility of that Watchdog Timer is to restart the system. That's what it does. Really, I mean, it doesn't do anything else. It waits until the time is up. When the time is up, it just restarts the system. What does that mean? If nobody touches this Watchdog Timer, it will try to reset the system. But we don't do that. We don't let that happen. So what do? every time I am running my operating system services, I am doing something useful, okay, I regularly reset the timer, okay? Every second, I reset that timer to 100 seconds. So that timer never expires at all, okay? If the system is running properly, since I keep resetting it, that timer never expires, so my system is never reset. If my system is not running properly, nobody is going to reset it. So my timer will expire and my system will be rebooted. So this is a way of making sure that if my system hangs, if my system crashes, okay, in 100 seconds I know that it is automatically reboot. Okay, it will automatically reboot in 100 seconds or 5 seconds, whatever. Okay, so that is a very good idea with the embedded systems. If they crash, okay, there is somebody watching it. We call it Watchdog Timer, and it will restart the system. It's a very good idea. It's used a lot. Okay. Any questions on this? You guys are hearing me okay? I am not talking to myself, right? Am I talking to myself?
Very clear, sir.
Oh, okay. Yeah, okay, people are there. Okay, good. So Watchdog Timers is another application for the clock hardware and software. And as we said before, profiling and monitoring statistics, I'm going to skip this because they are kind of obvious. One concern about the timers is since so many system components are using them, okay, so many system components are using them, the problem becomes this. We start to have too many interrupts, okay, too many timer interrupts, okay, one for the regular interrupt, the other one is for the timer interrupt. Şeyleri kullanmayın ya, onu kullanmayın. İnterneti. Tamam Ömer'e diyor. Ömer o elinde almış telefonu bir şeyler yapıyor. Okay, there was a problem with my connection. I think I am back. Okay, so we don't want this to happen. Okay, we don't want this. Too many interrupts is bad for the system performance. Why? Because I have to take the interrupt, possibility of full context switch. We don't like it. So the idea is the soft timers. Okay, if a timer interrupt happened, we will try to see if there is a coming up alarm. Okay, that alarm time may not be up yet. We might be a little bit early, we might be a little bit late, but that's okay because doesn't matter if I am going to wait 2 seconds or 2.001 seconds, okay? So instead, whenever the kernel is running for some other reason, whenever I made a context switch, I try to check if there is a timer expired, okay? I don't want that timer to create another interrupt because if it is real close or if it is has already expired, then I'm going to handle it. This is called soft timers. Why is it soft? Because it is soft because we don't create our interrupts at exact given times. Okay, it is approximate. These kind of timers will not cause interrupts, hardware interrupts, real hardware interrupts, but we will handle these kind of timers whenever somebody has made a system call, whenever some kind of other interrupt happens, such as the hard disk interrupts or the keyboard interrupts happen, etc. Okay, these are called the soft timers. and soft timers happens with system calls, TLB misses, page faults, IO interrupts, CPU going idle, etc. Okay, so idea is this: I could be a little bit late, 10 nanoseconds late to handle a timer, okay, alarm, but that's better than having spending our 30% of CPU time for handling the interrupts. Okay, you got the idea? Good. So I guess that's it about all I am saying with the clock devices and the software. As I said, they are important, they are very frequently used, and they are very irregular input-output devices. In fact, there is almost no information that you read from the timers. The important thing is that the timer interrupt has happened, and we use that a lot in our operating systems in many places. Any questions about the timers? Let me try to get this. There are people in my house now. Okay, maybe this is better. Okay, good. If there are no questions, then I will move on to keyboards, which is another popularly used input-output device, but I am not going to talk much about it. The structure of keyboard is very simple again in terms of hardware and software. Okay, the keyboard contains an embedded microprocessor on it. Okay, that microprocessor communicates with the controller on the parent board, motherboard, and on top of the controller, a special driver for the keyboard is run. And what is the function of that driver? Handling the interrupt caused by the keyboard and passing along that information to the upper layers of the operating system. That's it. Okay, and the rest of the operating system is independent of the keyboard type, is independent of the hardware of the keyboard. And basically that's it. I mean, if you like to go to detail, there is a lot of details, but that's beyond the scope of this course. Okay, so by the way, the keyboard doesn't talk about ASCII codes. Okay, all the keyboard say is that, okay, I have 101 keys. That's it, right? How many keys do you have on your keyboard? It's like usually around 100. Okay, so the keyboard reports that this key is pressed. That's it. Okay, it is pressed, it is released. That's it. That's what the keyboard does. The rest is handled by the keyboard driver. Okay, sometimes the keyboard driver works in the raw mode. Raw mode just reports the number of the key, but in cook mode, okay, it handles conversion to the ASCII characters or the Unicode characters, whatever. And if you do any like backspaces or delete keys, it does the deletes and that kind of stuff. So it depends on your operating system structure again, and I'm not going to talk much about it. Okay, move on. Another popular device is the mouse. Similar to a keyboard, mouse is an input-only device, and whenever you do something with the mouse, such as the movement of the mouse, or the clicks of left click, right click, etc., or with the later versions of the mice, you have the scroll wheel, right? The center wheel, the scroll wheel, and all that information is passed to the driver. Okay, as you know, mouse works in terms of delta values, in terms of positions. It doesn't report absolute positions. It reports relative positions, delta x and delta y. Okay, 40 times a second, it reports these numbers. It says that, okay, I moved this many units in X direction and this many units in the Y direction, and my button configurations are these. And it can create 40 times second interrupts. So that's a lot of interrupts. Okay, so the interrupt handling routine for the keyboard and the mouse has to be very, very efficient. As you see, many interrupts are happening per second on our computer system, and if you are not that careful in terms of efficiency to handle those interrupts, our system performance would degrade a lot. So most of the interrupt handlers are very simple. They don't even save many registers of the system. They just do whatever they need to do in a very short amount of time, minimal number of instruction executions, and they go back. That's it. Okay, that's the mouse part. And we talk about the inputs of, yes. I don't know how it is implemented in the I mean, if you are, I mean, many times changing those parameters actually are not doing anything to the hardware. They are just fake. Okay, the mouse is reporting 40 times per second. Sometimes they just ignore half of them. Okay, sometimes they get all that information, but they report a less resolution for you. Sometimes you set some of the registers in the mouse controller so that your mouse becomes more precise. Okay, it depends on your hardware, it depends on your drivers, and etc. I mean, the same thing for the cameras. Okay, they say that I am going to increase the resolution of this camera. Actually, the camera doesn't know about that resolution. The camera is not as capable as producing that kind of resolution. They increment the resolution. They increment the resolution in software by interpolating the stuff. With the mouse, if you like to do it, you can interpolate between two interrupts. Okay, cause some fake interrupts and produce it, and you would call it increased DPI. So the answer is depends on the hardware, depends on the drivers. The right thing to do is, of course, increase this time from 40 to 100. Okay, but your mouse needs to be that precise, and usually you cannot achieve very high DPIs using the mechanical mouse. Camera-based mice are capable of doing that kind of stuff. Usually very high DPIs are overkill for many people. Okay, good. If you look at the output software again to the screen, this X window system, which was developed in 1980s with a Unix operating system, okay, it's a very portable, very structured window management system. Okay, nearly all Unix systems base their user interface, graphical user interface, to the X window system. And in 1980s, this was standard for the Unix operating systems. If you have the graphical hardware, graphical screens, and etc. And it is a client-server model. Okay, your windows are your servers. You serve drawing of buttons, drawing of the scroll bars, and drawing of the other stuff. Okay, your application program asks the server to draw buttons, to draw scroll bars, to handle the mouse clicks, and etc. And all of them are served using this server stuff. Okay, most of the time this client part and the server part are on the same computer most of the time, but this system is designed in a way that this could be at different machines, because during those days in 1980s, these graphical displays were very, very expensive, and the terminals were still the norm. Okay, dumb terminals. What's a dumb terminal? Dumb terminal is just a keyboard and a screen. Okay, you type on your keyboard and your screen just shows stuff. All the processing is done at the central computer. Okay, if you need the graphical stuff, then you have the graphics terminals. Okay, again, this is a dumb terminal, doesn't do any processing. All the applications are run on the central computer. So the task of your graphical terminal is to feed all that, is to show all that information to the user. So it was done very portable way. Still, they are using the structured client-server model. Okay. And again, I am not going to talk much about this. It's a very detailed stuff. Nobody uses. Okay, this motif was a library. Here. Okay. It is used to make a graphical user interface programs with a uniform look and feel. Underneath there is intrinsics library. It manages the buttons, scroll bars, and etc. Xlib is the primitive set of graphical library stuff. It handles the mouse clicks and the keyboards and etc. So these were all libraries. And if you stop by my office, I still keep my books about motif intrinsics and Xlib. Each one is a 1,000-page long books. Okay, they are all books. And I keep them as doorstops nowadays. But if you like to see them, they are beautifully written by MIT staff. I don't think that they are colorful, but I think they have at most 3 or 4 colors. It's like the regular textbooks. They are beautiful books. Yeah, well, I'm not going to talk much about the X window system, but I like to show you this piece of code. Okay, this is a very simple hello world application written in C. As you see, it uses the X utilities and the Xlib. It doesn't use motif intrinsics. Okay, and it just shows this, not this one. It just shows a simple window, just an empty window. That's it. Okay, you make, okay, this is my server and this is my window. Graphics context, you remember from your Java. This is your pens and everything. Event handling, they all have to be handled by yourself and running. So there is a infinite loop somewhere. Okay, here. Running is 1. Okay, running is 1, and there is an infinite loop. So this one takes the events. What are the events? The keyboard events or the mouse events, and you handle them. We tried the same thing in, remember, in Java or C++. We register our event handlers, right? Well, in this case, we have to handle our events one by one. Okay, since there is no the inheritance in the original C language, we cannot say that I take this class and I extend it. Okay, we have to handle everything ourselves. So what we do, we copy paste this code and make modifications to it. How many lines of code? Maybe 60 lines of code, just to show ya ben ders yapıyorum burada, şey yapmayın ya, konuşmayın. Just to show simple empty window. Okay, so I think I am going to, no, I won't. Well, I mean, these are some details about the resources of the GUI stuff. But before doing that, no, I think I will stop. I am done with chapter number 5, IO. Okay, I will start a new chapter for the next 20 minutes. And I guess that will be very, very quick about the deadlocks. Do you have any questions about IO? And if you like to go back to the beginning of the chapter, that's what we said. Okay. Principles of I/O hardware, we did that. Software and individual devices, we looked at them one by one. You might say that, okay, we spent too much time on hard disks, mechanical disks. Nobody is using them at all. Well, which is true, but you know the rule, right? I mean, if you solve a problem with the computers, that problem will come back later. I am not sure if those problems will come back with the hard disks, but sure, we will see similar problems and we will have to solve those problems. Still, hard drives may not be used too often on our desktop systems or laptop computers or the portable devices, but they are definitely used a lot in servers. Okay, and server operating systems are a very considerable part of the operating system world. So those problems are still there. Okay. Any questions? Okay, if there are no questions, let me start talking about deadlocks. Okay. Since I forgot my pen at work, I won't be able to draw much stuff for today. That's why I am going to use whatever I had marked on my slides from last year. Chapter number 6, deadlocks. Okay, so the problem is this. I have two processes, A and B. Just to make it easy to remember, A is Alice, B is Bob. Okay, so both processes need printer and a scanner. I have two resources on my computer system. I scan a document and I print it. So to complete this task, what do? I scan the document and I print it. So the process A started doing this. It takes the scanner, process A, and it wants to use the printer. Process B just did the opposite. It takes the printer, it wants to use the scanner. So it is like this. A took scanner, needs the printer. B took printer, needs the scanner. So this is what we call a deadlock. They both have to stop. They cannot continue. Why? Because A needs the printer, B needs the scanner. They cannot continue because scanner is not available, printer is not available, but they are waiting for each other, right? So this is called a deadlock. Okay, and this problem is very common. It happens a lot in the computer world. Okay, so these resources like printers, tape drives, sometimes some specific records in your databases and etc. And for some reason, okay, we have some theories of it, but for some reason, operating system researchers, okay, they like to work on this deadlock problem a lot. I guess that's because the problem is very elegantly definable in terms of mathematics, like the graphs and etc. Okay, and they proposed lots of very compact solutions to this problem. And there is a very large amount of literature for the deadlocks. They studied a lot in the early days of the operating systems. They are just loved by the theorists. But in fact, for today's operating systems, nobody deals with the deadlocks. Windows ignores the deadlocks. Unix ignores the deadlocks. Linux ignores the deadlocks. They don't care about the deadlocks. Okay. So for me, deadlocks don't deserve a section in an operating system book, but there is a section about it, and many different methods in it. I am not going to talk much about deadlocks. In fact, I never wanted to talk about the deadlocks, but when you go to some job interviews or maybe graduate school interviews, okay, They will ask you about the deadlocks. So you need to know a little bit about the deadlocks. If you like, you can read the whole chapter. If they ask you about the deadlocks, you will tell them that why do you need to know about the deadlocks? Nobody uses them, okay? Ask them what Windows or Linux or Mac OS uses for the deadlocks. The answer is they just ostrich algorithm. You know what ostrich algorithm is? You know what ostrich is? It's deve kuşu in Turkish. Okay. So the ostrich algorithm is stick your head in sand until the dangerous situation is over. Okay. When you take your head from the sand out, everything will be fine. So ignore the problem. Okay, ignore the problem. That's what the operating systems do nowadays. Okay. That doesn't mean that deadlocks are not important. They are important, but they are not handled by the operating system software. It is usually handled by the application level software, for example, the databases. Okay. In a database, deadlocks are important because each record has to be locked before they are updated. If two different processes are trying to lock the same set of records, there is going to be deadlocks. In that case, it is real. But for the operating systems, usually there are very good ways of preventing this kind of deadlocks by design. And we are going to look at some of them. Okay, usually deadlocks and live locks. Okay, there is a concept named live lock. Does anybody know what live lock is? There is a deadlock and there is a live lock. Let me show you a live lock example. At the end of the chapter, important stuff. Okay. So this is a live lock example. Okay. Process A acquires resource 1 and it tries to acquire resource 2. Okay. If it is not available, then it releases resource 1 so that if anybody else needs resource 1, they can take it. Then I wait a fixed amount of time and I will try to get the resource number 1. Okay, so this looks smart, right? This looks smart. Why? Because it never takes resource 1 and keeps it, okay? It always takes it, tries to take the resource 2. If it cannot take it, then release it. So this will never cause a deadlock, okay? Because there is no, I am holding this and waiting, okay? It always tries to get the resources one by one in that order. But this may cause a live lock, such as, suppose I have two processes, process A is running at the same time, okay? Okay, they have the same thing, okay? Process A and process A. This one started taking resource number 1 and resource number 2. Okay, this one. So this one took R1, this one took R2. Then this one tried to get R2, failed. This one tries to take R1 and fails. Both of them failed. Both of them released their resources. Both of them waited a fixed amount of time and they tried to acquire again. So they are running this loop over and over again. They are live, they are not waiting for each other, but they cannot continue to execute the useful part. They keep running the same thing. They are taking the resources and releasing them, taking the resources and releasing them. This is called live lock. Okay, this is called live lock. This is not seen as often as deadlocks, but this can happen. How would you solve this problem? Just make a simple change in this code and this problem will be fixed. Any ideas? Very simple fix. Well, that prevents the deadlocks and live locks altogether. No, I am not talking about it, but that's a good idea. Instead of waiting a fixed time, if I wait a random amount of time, right? So this one will wait 1 second, this one will wait 2 seconds. While this one is waiting, I will take resource 1 and I will take resource 2 and I will continue, right? So instead of waiting fixed amount of time, wait random amount of time. This might solve the problem, but it is not unusual that they are picking the same random number, and because they are using the same pseudo random numbers, right? It may go on. Okay, so this is called live lock. Deadlocks, live locks, and starvation. Okay, starvation is another concept. What is the starvation? Okay, the starvation is this, and I think I gave this example before. Okay, if you are the printer server, what would you do? You will say that I will print the shortest file first because that's the fastest. I will complete that task first. I will make that user happy, and I will make the longest job wait. If you keep doing this, that longest job will never get served if the system is busy. That's called starvation. This is not deadlock. This is not live lock. Okay. Somebody is getting served all the time with the starvation. Okay. But some of the processes are not getting served at all. This is called starvation. Okay. So keep the definitions in mind: deadlock, live lock, and starvation. Okay. That was the end of the chapter. Let me go to the beginning of the chapter again. Okay, deadlocks and live locks. Okay, most operating systems basically just ignore the problem. Okay, so because preventing deadlocks and live locks will require lots of controls and checks, and that will take lots of CPU time and a significant amount of operating system design effort. We don't like that. So our operating systems are not perfect. We get hangs and we get crashes once a week, once a month, right? So I am okay. I mean, if I get a crash, operating system crash, okay, once a week, once a month, and usually these kind of crashes happens not because of the deadlocks or the live locks, some other purpose. And if I get one more crash due to a deadlock, that will be fine. It will be better than my operating system is going to be 20 million more lines of code or 10% slower than it used to be. Okay. So the problem is this: the price is high, and whatever you are getting, if you spend this money, if you spend this effort on preventing deadlocks or live locks, okay, you are not getting much in return. So you are trying to prevent something that's going to happen once a month, maybe. Okay, so thus we are faced with an unpleasant trade-off between the convenience and correctness, and a great deal discussion about which is more important and to whom. So we ignore the deadlocks and live locks. Okay, so that doesn't mean that we are going to completely ignore it in our course. I am going to spend at least half an hour on it. But as I said, there are many people who think that deadlocks are important for operating system and know about it. Okay, so definition of a resource: printer is a resource, scanner is a resource. Okay, CPU is a resource, memory is a resource. Okay, hard drive is a resource. They are all physical devices, database records, shareable things, mutexes. These are all resources, system resources. Preemption is something, okay? Preemption is something that would prevent deadlocks. What's a preemption? If a process is using the CPU, as an operating system, if you get to say you use CPU too much, too long, I am going to stop you. This is called preemption. You take away the resource. Okay, you take away the resource. So if the operating system say that, okay, I'm taking away this resource from you. No deadlock can occur. Okay, remember that the process A and B, Alice and Bob. Okay, if Alice can take the printer from Bob, then there is no deadlock, right? But you cannot take away the printers from processes, because if the process is printing something, you cannot stop that process in the middle and stop the printing process. Okay, it has to continue once it starts. Okay, so some resources cannot be preempted. Some resources cannot be preempted. CPU can be preempted because we keep doing that all the time. How about this? How about is memory a preemptive? Is memory preemptible? Preemptible? Can I preempt the memory from a user? From a process, sorry. Yeah, that's the that's the perfect answer, Usama. Yeah, we spent at least 4 weeks on it, right? I mean, how we share this memory, how we do the swapping in and out pages. Yeah, we do that. I mean, if you have the paging, if you have the segmentation, of course we do that. Okay, if we say that I need this memory, I am going to swap you out to the desk, and I will continue. Yes, memory is preemptible. Okay, but some resources are not preemptible. Okay, if the preemption is available, then there is no deadlock. Okay, preemptible and non-preemptible resources, the deadlocks happen with the preemption. Okay, and what else? Oh, okay, so this is a good way of showing a resource acquisition sequence. This one is very simple. To use the resource number one, I down the semaphore, mutex. Is the semaphore? Yes, a semaphore. I down this resource, I use it and up it. If I have two resources, I down resource one and resource two and use it, use both of them and up them. Resource acquisition. Good. Okay. So this one is a deadlock free code A, but this one is not. Let's look at this one. I have two semaphores, two resources. Down resource one, down resource two. Use it, up and up. Process B is doing exactly the same thing. There cannot be a deadlock with this system. Why? Because they are taking these resources in the same order. The situation is not the same for this part B. Why? Because process is taking the resource 1, then resource 2, uses them both and releases them. On the other hand, process B starts taking resource number 2 and resource number 1 later. So it switched the resource allocation order. So let's look at this one. Let's say process A took resource 1, an interrupt happened. I switched to process B. Process B took resource 2. Okay, so this is the case. Process A keeps resource 1. Process B keeps resource 2. This one will be blocked here and this one will be blocked there. So they are waiting for each other. Situation will be shown like a graph. A and B are processes. Okay. Process A took resource number 1. Process B took resource number 2. B needs 1, A needs 2. So there is a circular path here, cycle. This is called the resource graph, and we don't like the cycles in the resource graphs. They indicate deadlocks. Okay, so basically deadlock detection is something like this. You form a graph like this in your kernel space every time when you make these kind of resource allocations, and you continuously try to detect if there is a cycle in this graph, which might seem simple enough, but usually our deadlocks don't happen between these two simple processes. It happens between many processes and many resources. Let me show you one example. For example, this. Okay. There are 1, 2, 3, 4, 5, 6, 7 processes, and I think 6 or 7 resources. And as you see, there is a cycle here. This part of the graph has a cycle. Well, of course, we can run some efficient algorithm to detect this cycle, and we say that there is a deadlock. So how do you stop this deadlock from happening? Maybe preempt this resource, maybe terminate this process, etc. I could do that, but it will take time to form this graph and run this detection, etc. And this doesn't happen often, so why bother? That's it. Okay. So your operating system sees only this. Operating system says that, okay, I have 1, 2, 3, I have 7 processes. They want to do this. Is there a deadlock somewhere? Okay, is there a deadlock somewhere? Yeah, the answer is yes, there is a deadlock here. But as I said before, I am not going to go into these kind of algorithms. But I mean, using the resource graphs, these are trivial to detect and trivial to prevent. If you have time to run these kind of algorithms in your operating system's time. Okay, good. I think I am out of time. If you have any questions, I will take the questions. Otherwise, I will stop here. Tomorrow, I will finish up with this deadlocks, and I will start talking about the chapter number 7, which is more important, virtualization clouds. Okay. And I think I will finish up with the semester tomorrow. Any questions? Any questions? Okay, if there are no questions, that's it for today. See you tomorrow morning. You too. You too. Thank you. Bye.